Hello everybody, welcome back. This video is based off of information from Unit 1, Section 10 of AP Calculus, exploring types of discontinuities. And we've kind of reached just getting beyond the midway point of our first unit on limits and continuity. We've learned all about limits, and now we're going to focus on continuity and the implications of continuity and all of those kinds of situations. In this lesson, we're going to look at different types of discontinuities, the major types of discontinuities, and then look at some ways to identify discontinuities from functions and graphs. Okay? Before we can talk about discontinuities, though, basic idea. We need a basic idea of what it means for something to be continuous. And we start here, we're going to refine this, but we start here with the idea that a function is continuous if it can be drawn without lifting your pencil off the paper. And that's, a basic kind of, like I said, very intuitive standpoint. So for instance, if I draw a curve like this, that was continuous because I could draw it without lifting my pencil off the paper. A curve like this is not continuous because obviously you saw me lift my pencil off the paper or my stylus off the screen as I transitioned at that portion of the graph. So that gets us started with an intuitive idea of what continuity is. So let's start looking at the types of discontinuities. The first type of discontinuity is what's known as a removable discontinuity. We call it removable because it's a discontinuity that could be fixed by adding a point that doesn't exist, or by moving a point that does exist to a different location. And that's what you see in both of these pictures here. You see this curve with the little hole right here, and in the second curve, same curve with the hole there, but there is a function value elsewhere. So we could either fill in that hole or move the point to the hole, depending on if we're looking at the left graph or the right graph here. Key characteristic, what you see in bold here, the limit exists at the location of the point of discontinuity, but it isn't the same as the value of the function there, or the function doesn't exist there. So what you see in both of these graphs, the limit exists as, let's call this A. The limit exists as x approaches A on both of these graphs. However, in the graph on the left, the function doesn't exist at A. And in the graph on the right, the value of the function is not the same as the value of the limit at A. So that's what removable discontinuity looks like and the basic characteristics of it. Next, a jump discontinuity. We're so clever as mathematicians the way we name things. Jump discontinuity is a discontinuity where the function jumps at a particular value of x. The key characteristic related to limits of a jump discontinuity is that both the left and right hand limits exist, but they're different. The function is approaching a different value as we approach that x value from the left than it is approaching as we approach it from the right, and so we see a jump discontinuity there. Infinite discontinuities, which you've studied before, know them better as vertical asymptotes. Those are discontinuities where the function approaches an infinite value on at least one side. In the picture that I have here, it actually approaches an infinite value from both sides. The left-hand limit is approaching positive infinity, while the right-hand limit is approaching negative infinity. And what we have when we have an infinite discontinuity is either the left or right-hand limit, or both, approaches either infinity or negative infinity. That's how we can talk about it from a limit standpoint. Now, are there other types of discontinuities? Yes, there are, but these are the three that are by far the most common. And, maybe if I have a little bit of time at the end of this video, I'll show you an example of what they call an oscillating discontinuity. Okay, so let's go ahead and look at a couple of examples here. First, a graphical example. We are going to identify the location and type of discontinuities in this graph. Okay, So, looking at this graph, I see 1, 2, 3 discontinuities. In fact, I see one discontinuity of each type. So, first of all, at x equals -2, this x value right here, we have a discontinuity. It's the kind of discontinuity where the limit exists, the limit from both sides is the same, but the function value is not the same as the limit. And so here we have a removable discontinuity. The next place where we have a discontinuity in this graph is over here at +2. At +2, the limit from the left and the limit from the right both exist, but they're different. And so here we have a jump discontinuity. And then over here at 4, we have our third discontinuity. As x approaches 4 from the left, it's approaching -infinity. So the limit approaches an infinite value from one side, either positive or -infinity. So we have an infinite discontinuity here. Okay, let's go on to example 2. Find all the points of discontinuity of the function and identify the types of discontinuities that exist in the following function. One of the key characteristics that we're going to look for, and you should already have kind of learned this idea in a previous course, Algebra 2 or Pre-Calc or both, where we're going to look for discontinuities. You know, if you think back to what you've done, you know, when you were looking for vertical asymptotes in earlier classes, what you did was you looked at the denominator of this rational function, and you looked for where it was equal to 0 to identify where asymptotes were. And in reality, that doesn't tell us where asymptotes are. That tells us where discontinuities are. Sometimes those discontinuities are asymptotes. But I'm going to set that equal to 0, that denominator equal to 0, and solve for x. And these are the locations of our discontinuities for this rational function. Now we still need to identify the types of discontinuities that exist. In order to identify the types of discontinuities that exist, we're going to use the limit characteristics that we talked about with all of these. For instance, if the limit exists, but it's different from the function value, then we have a removable discontinuity. If the limit exists from the left and from the right, but those values are different, then we have a jump discontinuity. If the limit approaches infinity from one side or the other, then we have an infinite discontinuity. So what I'm going to do is I'm going to look at the limit as x approaches both of these values from the left and the right. I'm going to abbreviate with f of x here just to save myself from rewriting that whole function in my notation. But we're going to examine what happens with these limits, and it's probably going to be easiest for us to examine what happens with these limits quickly and easily by just making ourselves a quick table of values on our calculator. So that's what I'm going to do. I'll pull up my calculator. And enter in my function, which is x squared minus 3x minus 40 over x squared minus 6x, minus 16. And I'm going to set up my table to find the limit as x approaches 8. And then I'm going to go ahead and look at my table. And it appears that as x approaches 8 from both sides, this limit is 1.3. And then I'm going to go ahead and find the limit as x approaches negative 2. And as it approaches from the left, the function approaches negative infinity. And as it approaches from the right, the function approaches positive infinity. Okay, so all this information tells me everything I need to know about the discontinuities in this function. There is an infinite discontinuity at x equals, or vertical asymptote, infinite discontinuity or vertical asymptote at x equals negative 2. And then this one, the limit exists, so that makes it a removable discontinuity. And that actually tells us the location of the point. If you think back or look back at our removable discontinuity on the first page of this lesson, you notice that it was just a hole in the graph. So we indeed have a removable discontinuity at the point 8, 1.3, where there's a hole in the graph. All right, that's the end of today's lesson. There's some problems for you to practice on over the next couple of pages. And there, for those of you who are my students, there's a My AP assignment that you want to make sure you get to. Now, before I sign off, I am going to, I said I would, so I'm going to show you an example of an oscillating discontinuity, which is another type of discontinuity, which is kind of rare. I can do it with a relatively simple function. We'll graph the function y equals sine of 1 over x here. And as x gets closer to 0, you can see here that the graph gets kind of bunched up as we get close to 0. Now, if I zoom in on this, you'll notice that the function just continues to oscillate more and more and more the closer I get to 0, to the point where the graph almost looks like it's just a shaded in box. I will tell you it's not, and as I zoom out more from here, you can see how that kind of spans apart. But as I get closer and closer to 0, the function just goes up and down faster and faster and faster. And that produces what's known as an oscillating discontinuity. Like I said, that's a rare bird compared to the others. You really need to make sure you understand the background behind the removable discontinuity, the jump discontinuity, and the infinite discontinuity. All right, see you all next time. Have a great rest of your day, and we'll be back next time with section 11 from Unit 1. All right, have a good one.